So how many of you have been able to do both the iterations? Please raise your hands. First, how many have done for iteration 1? Please raise your hands. Both the iterations? Okay. So here is the result, first iteration, and this is the result of the second iteration. Please check that your results match this. Are you getting the same results? Anyone has something different? Okay, so if this is the result, then let's start making some interesting observations. Okay, observe that here at the out of 5, nothing is live, right? And we are making an assignment to A, and A is not live at the out of 5. What do you conclude? It's a dead code, right? So we can get rid of it. So if we do this, so we can repeat the liveness analysis. Okay, so we can eliminate this and repeat the liveness analysis. If we eliminate this, you will observe that then, I think I have it on the next slide. Okay, so we can repeat liveness. So the point is, you done an analysis and now you are optimizing the code, you are changing the code, because of which some results of analysis will change. So you can repeat the analysis, you can once again do the optimization, you can once again repeat the analysis, keep doing it as long as you want. That's not how practically it happens. There is some other analysis called strong liveness analysis, which does it in one fixed point computation, one way of in one round of computing the result when the result stabilize, but we will not look at it because it's an advanced analysis. But we will show here what happens repeatedly. So let's say I have now deleted this. Okay. Now what will change here now? Which result will change? Can you just go to your results and say where will the change be? Tell me what will be the change? The out of 5 does not change, the out of 4 will change, and everything else will change. In of 5 will change, yes, in of 5 will change. So in of 5 now will be A and B. Earlier we had C, right? So now that C is gone, right? Yes? So C, that's the only change. C will not be live anywhere, right? So you get this result where you just removed C from everywhere. Now we can do further optimization. Once again observe that out of 5 is still empty and there is no use of T1, right? So you can repeat liveness analysis. What will happen now? A and B, we will do this dead code elimination, T1 equal to A plus B. So how will your liveness result change? How will it change? Please look at your result and tell me what will the change be. A and B will not be live here. So A and B will not be live here. A will be live here. So the liveness of B goes away from everywhere, right? So we get this result now, okay? And assuming that because we are there is a side effect of printing, we can't optimize away these blocks. So this is the final result that we get. So you can see the only thing that is live here is A, nothing else is live, right? Yes or no? M is, of course, M is live. Only M and A are live. B, C are not live because B and C were used only in block 5 and we have got rid of them as dead code elimination, right? So, let's just now step back a bit and understand what we have been doing. Okay, so we have to define an analysis, we have to formulate, define an analysis, give a formal definition, and then give a formula, give a set of equations. So we formulate the analysis and then we perform the analysis. So in order to define the analysis, we define the properties of execution paths, we define the data flow equations, which are linear simultaneous equations on sets and not numbers. And so here the domain of values is sets, and later we will see later in the maybe not here, but it's possible for us to generalize the domain of values. Okay, and performing the analysis, so solve data flow equations for a given program flow graph, right? And there are many unanswered questions. What should be the initial value? So we started with empty set as the initial value. Is that the right value? Can some other value be used? Will the analysis terminate? What will be the complexity? How many traversals will be needed? What is the properties of solutions? What are the different, can there be multiple solutions? Is one solution better than the other solution? So these are the important questions which we will obviously not covered formally here, but I want to hear your intuitions. We'll talk about initial value later. Let's talk about termination. Do you think live variables analysis will terminate for every program? Can there exist a program for which live variables analysis would not terminate? What are the conditions, what are the properties that govern termination of live variables analysis? Yes, so the point is the analysis terminates when there is some iteration I in which the data flow values that you have got, the sets that you have got are same as the sets that you got in I minus 1 iteration. The question is, does there exist such an I such that the data flow values of I and I plus 1 or I minus 1 and I are same? Can you give me some reasoning, some intuition? I am not asking for a formal proof, but can you say yes, maybe because of this reason it will happen? So for that you have to think of a program. Yeah, go ahead.
Maybe there's a program that switches, like that in every iteration switches maybe one variable between dead and alive.
How can that happen? How can we have a program that does that? So his contention is maybe there is a program in which a variable A becomes live in one iteration and then becomes dead in the other iteration. Can that happen? Can there exist such a program? So I am saying that we are not doing any dead code elimination yet. Okay. So let's assume we are not doing dead code elimination, we are talking only about one round of live variables analysis. Program is not changing. Let's assume program is not changing. Then what happens? So the question is, if a variable has been declared to be live in one iteration, can it ever happen that it will be found to be dead in the next iteration? That's the most important question. So if you have found it to be live in one iteration, it means that you have found a path from use to this point in which the variable is used, right? That's why it's live in one iteration, right? Now you're not changing the program. In the next iteration, does that path go away? No, the path will remain, which means that if a variable has been declared live in one iteration, in all subsequent iterations it will remain live. Very important property. No, in every iteration you're supposed to traverse all nodes. Right? It's not that you're going to exclude some path. So the whole point is this. So her question is it possible that I have not covered one path in one iteration? That's a good question. That's a very good question. Let me try and answer it. I'll give you an example where some path is not covered in one iteration. Yeah? Exactly. If it's a loop, then you have not covered the path that starts at the loop entry. So for example, if you have a loop here and here you have use of V, so here you are not marking V as live in the first iteration. Okay, but that's not the situation that we're talking about. We are not asking whether a variable is not live at a point, can it become live? We are asking some other question. The other question that we are asking is, let's say I have marked V as live here. Can it ever happen that it will be dead in the next iteration? So if we have marked V as live here, it means that we have found some path where there is a use of V and the use of V reaches here. Right? Now that path is not going to change. Right? So if you are doing a systematic analysis of traversing the nodes in the same order. So if you have traversed this path in iteration I, in I plus 1 also you will traverse. You may discover new paths in an iteration, but you will not miss out a path that you have considered before. So therefore, if a variable has been declared to be live, it will remain live. Mathematically, data flow analysis is monotonic. The changes are monotonic. So what's going to happen is that you start with an empty set, and at every program point you have an empty set as a solution, and now your sets can grow. They can only grow. So once you have a set, that set is not going to become smaller. It can only grow. Now can you answer the question of termination? Yes, so your set could be expanded, your set may keep growing. The question is, can it grow infinitely? No, because your number of variables is fixed, right? So the fact that you have a finite set of variables and the fact that the growth is monotonic, it means that this analysis will always terminate. Right? It will always terminate. In how many steps would it terminate? That's a slightly longer question. We will not address that. But it's possible for us to give a complexity measure. We can talk about the number of iterations, maximum number of iterations that would be required to terminate this analysis. So that's the question of termination. Initial value. So remember, now we are saying that if we have a set V at a program point, we can get a superset of that, but we are never going to get a subset of that. So suppose we begin with the initialization as a superset. Suppose instead of empty set as the initial value, we declare all variables to be live everywhere. Okay, what will happen? So what will happen is you will once again stabilize, you will once again get the a value, the value may be different. So you can have different results. So if you do linear simultaneous equations and depending upon the initial estimate that you have, you might get different solutions. Okay, theoretically speaking, we say this solution is a fixed point. So for mathematically this is formalized as all these values become values in a lattice. How many of you heard of a lattice? Discrete structure course everyone has done. But have you covered a lattice? Have you heard of a partially ordered set? Yes? So a lattice is a partially ordered set, right, with certain properties. Okay, we will not get into the details, but there is a very nice mathematical formulation of this. All the values that we are computing are elements of this partially ordered set, are elements of this lattice, and then the functions that we use to compute this are monotonic functions, and therefore we compute the fixed point of functions. Fixed point of a function f. So what is the fixed point of a function? Mathematically, fixed point of a function f is some value x such that fx is equal to x. So when you have an iteration after which you get the same value, you have reached a fixed point. That's the technical name for it. Now the point is, we say technically speaking, we will definitely reach a fixed point if the set of values forms a lattice and functions are monotonic, but we may get different fixed points. There can be multiple fixed points for a function and we may get multiple solutions. Now that's something that we are not going to look at in greater details. Instead, what we will do is we'll look at the next questions. Yeah. So so I think this is okay. So this is the algorithm, round robin iterative algorithm. It's basically what it says is this is what you are doing. So you initialize everything to empty set and then you say while there is a change, you iterate over the graph completely. What do you mean by iterating over the graph? For every node n, compute out n from its successors and compute in n, and if temp is same as not same as in n, you say okay there is a change, so you need to go over it once again. So this is the algorithm that you were using intuitively. I did not show you the algorithm before. I just wanted you to discover it on your own, right? So this is what we do in solving data flow analysis. Okay, another tutorial problem. Draw the control flow graph and do live variables analysis for this tutorial problem. I'm going to make you solve lots of problems, so you have to work them out. this got pressed here. So it is splitting it in different blocks. It's okay. That's okay. Any people have drawn the control flow graph? Okay, very good. Is this the graph that you're getting? Mm-hmm. So what is the question? No. Yeah. Can we move increment of I to block number 2? I is equal to I plus 1. Can we move it to block 2? No, no. First, let's do one by one. Can we move I is equal to I plus 1 to block number 2? That's the question. No, because you don't want to use the updated value in node 3. So, this condition, this increment is always executed at the end of the loop, not at the start of the loop. Right? So, I mean, you might transform the program saying I'll initialize I to something else, but that's you're changing the program. This is the default loop control flow graph that we will create. The structure of for loop is you do the initialization, which is this, then you check the condition. If the condition is satisfied, you have loop body. At the end of the loop body, you have the increment. Right? Okay. So, what do we have next? Yeah, so I have these data flow values, but I would like to, I want all of you to solve this problem quickly. I don't want to rush. I don't mind omitting a topic, but I want to make sure that you understand something well enough. So please give me the result of live variables analysis. You have the equations with you now. Please give me the result of live variables analysis for this. Okay, very good. So let me show you the result. So this is the first iteration. Just check if your result is same. Anyone is getting a different result? Are you all getting the same result of the first iteration? Yeah? In block number 1, why is the liveness of A not killed? Someone tell me why is the liveness of A not killed in A1, in block 1? Block 1. I mean, are we redefining A in block 1? For liveness to be killed, the variable needs to be redefined. We are not assigning a value to A, right? So you might, so the point is there is a path from here to here that goes from here. Program may not execute like this. You might say if it goes like this, what is the value of A that it returns? It may be undefined. But as far as we are concerned, A is live on entry, right? Okay. So what will change in the second iteration? Can you look at the graph and tell me what will change in the second iteration? Block 5. What will change? Out of 5 will be enough 2. What will we mark as? What will become live there? A, N, I, K. All of them will become live. Right? Now you are developing the intuitions that I want you to develop. Right? So this is the change in the second iteration. This is how the values will change in the second iteration. Just make sure that you understand them before we go to the next problem. Does this look fine? Anyone has a question? Does this seem okay? Does anyone have a question about this? Are you all understand how do we get this result? Uh-huh.
For out, are we getting AIN? Like
In the second iteration?
both it is getting killed, right?
No, so which one are you saying?
Third out.
In yeah? Okay, so let's move on. Okay, now answer these questions. In this graph, is the same graph that we have solved, for which we have performed analysis. Is A live at the exit of node 5 at the end of iteration 1, and why? Is it live? Yes. Why? Is it live? No. Why? at the end of iteration 1. So that's the question. Is A live? So is A live here at the end of iteration 1? No or yes? Yes? How do you get liveness of A here? First iteration. I'm not saying in the final result. In the first iteration, you're going to compute out of 5 from in of 2. What is in of 2 in the first iteration? Empty. So therefore the answer is A is not live. Right? Okay. Is A live at the exit of node 5 at the end of iteration 2? Yes. Show an execution path along which A is live at the exit of node 2. Now in the final solution. So show me a path starting at 5 along which A is used before being defined. So give me the path starting from 5. 5 to 6, yes. So 5 to 6 is one path. Is there any other path? Huh? Yes. 5, 2, 3, 5 is another path. So there are multiple paths. Right? Good. Show an execution path along which A is live at the exit of node 3. Execution path. So starting from 3, what is the execution path? So obviously this path. Yeah? Yes. Yeah, so start from 3, go to 5. So therefore A is live here because of this path. Any path that involves this edge. Because in 4 this is killed. A is killed. Right? Of course, when we talk about execution path, we begin at the start of the program. Okay? Show an execution path along which A is not live at the exit of 3. 3 to 4. When you take any path that takes the edge 3, 4, that's a path that satisfies this. Okay? Very good. Now write a C program for this control flow graph. So in the previous question you were given a program and you wrote a control flow graph. Now you are given a control flow graph. Give me the program corresponding to this. You are not allowed to use go-tos. Yes. So I already have an answer. Anyone else who has written the program? Is all this too much of a mental gymnastics for you? It's good for you. If something पैकेज कहाँ से आएगी? How will the control go from N5 to N3? There's a loop there. You don't have a loop in your program. Yes, this is correct. Yes, this is correct. So let me show you the solution. Yeah, this is the program. Please check if your program matches this. There is no function call here. There is no function call here. We are doing intra-procedural analysis, so there are no function calls. If you introduce function calls, then we do inter-procedural analysis, for which you have to come to IIT Bombay and do my course CS 618. Not here. Is getting a different program? Are you all getting the same program? Do you all see why this is the right program? Okay, what do I have now? Solution of tutorial problem 3. Maybe we will leave this, we will proceed. So the solution is here, you can work it out. Now let's just see, let's answer these questions. So the claim is Z is live at the exit of N5. The question is why? Show me a path starting from N5 in which Z is used before being defined. N5, N5, N3, N4, that's right. Okay. Why is Z not live at the entry of N5? Because Z is redefined in N5. Wonderful. Why is X live at the exit of N3 in spite of being killed in N4? Why is X live here in spite of being killed here? Yes, because there is a path N3, N5. in 6. Right. Okay. Uh-huh. No, this is x, not z. Right. Okay. So identify the instance of dead code elimination. Do you find a dead code here? So we have not done live variables analysis, but can you use your intuition and say that here is an assignment whose value is not required anywhere? Uh-huh. Y is equal to 2 star z. No, this value may be required here. Z is equal to 1. Z is equal to 1 value. Yeah, Z is equal to 1 is not required. Oh yeah, it's required here. Uh-huh. X is equal to 1. X is equal to 1 is required when you come along this path. Uh-huh. Everything is x is equal to y plus. Where is x is equal to y plus 2? X is equal to y plus 1. This one. This is required here. X is equal to y plus z. This is required here. Last statement is the one that is dead. Yeah, right? I hope you are having fun, right? So these are the kind of questions that you should be able to. Yeah, of course. Subsequently, you can do lots of things, but in this program, right? Okay. Fine. Let me just skip these questions because we have not done liveness analysis for this problem. Yeah. So now let's come back to some general concepts. Now we have seen analysis, we have worked out some tutorial problems. So we have to talk about, so there are these important requirements: soundness, precision, efficiency and scalability. So the point is, static analysis results are going to be inexact because static analysis is undecidable. And as we said, undecidability means there cannot exist an algorithm. It's not that we're waiting for some brilliant person to come and give us this algorithm. We cannot have such an algorithm, no matter how brilliant someone is. Okay. So possible reasons of undecidability: because values of variables are not known, branch outcomes are not known, there could be infinitely many paths in presence of loops and recursion, there may be infinitely many values. So typically undecidability intuitively means one of these two situations happen. Either you get paradoxical results, either you get results that cannot be true simultaneously. If this is true, then this cannot be true, or this is true, this cannot be true, and you say both of them are true. Either that, or you get into infinity, you get into infinite computations, meaning the computation is never going to terminate. So intuitively, these are the things that cause undecidability. Okay. So what happens is, static analysis result is inexact. What does that mean is that the predictions may not match the actual runtime behavior always. There may be some runtime behaviors where the predictions may not match. Now there is a problem. The problem is, if we cannot get exact results, if there is a run where the result does not match, does it mean the result is wrong? That's the question. The question that we have to ask is, if we are saying that this cannot match, then is the result wrong? So there is a notion of something being wrong and there is something being correct but conservative. So what happens is, so let's look at this. Some predictions may be erroneous because the predicted behavior may not be found in some execution instance or may not be found in any execution instance. These are the two different situations. Either there is no execution instance where this behavior is found and you say that you predict that behavior, or there is some execution instance in which the behavior is not found, but there is some other execution instance in which the behavior is found. So when we say error, we basically mean mismatch between runtime behavior and predicted behaviors. Now it turns out that some of these errors may be harmless, whereas some of these errors may be harmful, and that's the distinction that we wish to make. Some errors may be unavoidable because of undecidability. So how do we characterize, detect and minimize these errors? So we have to look at this notion of there is an error but this error is harmless. There is an error but this error is harmful. And there is an error and I cannot avoid this error. Or there is an error and possibly I can avoid these errors. So these are the kind of things that we want to look at. So again, when we say an error, a guess leading to an action which is different from the actual reality. So these are some intuitive examples of harmless and harmful errors. Okay, for example, you're talking about medical diagnosis. So if you subject a person to further investigations, it is in general harmless. It may be an error, but in general it is harmless unless the diagnosis itself requires you to take something that is harmful to the body. Okay, so you have a suspicion and doctor says, okay, go and do your x-ray and we'll rule out. Maybe after doing x-ray, doctor says, actually there is no problem. That's harmless, assuming x-ray doesn't harm you too much. I mean, for example, if you are pregnant ladies, x-ray would harm. So in the situations where in some situation there may be an error, but that error may be harmless. Okay. On the other hand, avoiding further investigations even after suspicion, that could be a harmful error, right? Similarly, for establishing justice in criminal courts, starting with the assumption that an accused is innocent is harmless. That's considered the wisdom. To begin with, that an accused is harmless, and then you prove that accused is actually not innocent, right? So starting with the assumption that accused is guilty is harmful. There can be many more examples. I mean, the checks that happen at airports, subjecting everyone to serious checks is problematic. It may be erroneous, but it's harmful. But saying no, because of that I won't check anyone at the airport, now that could be a harmful error, right? So similarly, in static analysis, some errors are harmless and some errors are harmful. So for static analysis, harmless errors can be tolerated and should be minimized, and harmful errors must be avoided. So let me see, what do I have next, then we'll come back to So let's take live variables analysis. So in case of live variables analysis, our application is doing dead code elimination. Give me an example of a harmful error in liveness analysis and a harmless error in liveness analysis. So I am using liveness analysis for dead code elimination. What does dead code elimination say? I have an assignment x equal to something and I am asking the question, is x live here? That's the question that I am asking. And supposing I make a mistake in asking that question, what kind of a mistake is harmful and what kind of a mistake is harmless? So yes, removing an assignment which is used later. So let's say I have x equal to, let me actually use the board here, I don't have it on the slides. So I am saying the situation that I am trying to characterize is this. So I have an assignment x equal to something. Okay, there are two situations. One is x is actually live, but analysis does not find it to be live. This is one example. Second is x is not live, but the analysis finds it to be live. These are the two possible mismatch in the predictions. Reality is here X is live, my analysis says it's not live. The reality here is X is not live, but my analysis says it is live. Which one of these is harmful, which one of these is harmless, or both of them are harmful or both of them are harmless? First one is harmful because we may end up deleting an assignment, and this is harmless. Same thing happens for register allocation, right? Okay, actually in register allocation you may not put something in register. Now the point is here you might say that this decision is based on the application, but it turns out that these results are independent of the application. There is a very nice beautiful theory which again, I'm sorry I keep saying this, we are not going to cover in this course. So I mean I spend about 3 or 4 weeks on the theory of data flow analysis, where from mathematical perspective and intuitive perspective we say doesn't matter what the application is, declaring a variable to be live when it is not live is okay. It's an error, but it's a harmless error. But declaring a variable to be not live, declaring a variable to be not live when it is live is actually harmful. So soundness deals with not making harmful errors, precision deals with not making harmless errors. So if you make harmless errors, maybe you get result which is not very precise. Maybe you will not be able to do dead code elimination that you should have been able to do. That's where you're losing on precision. That's where you're not getting as much benefit as you would have got, but still things won't go wrong. But if you have harmful errors, then we are compromising on soundness, right? I would like to leave this topic at this intuitive level here. We won't be able to go into the mathematics behind how do we characterize mathematically precision and soundness. Okay, so efficiency, scalability, let me just skip this. Yeah, so let's come to termination, convergence and complexity. So we talked about it. For live variables analysis, the set of all variables is finite, the meet operation is union, and hence the set associated with the data flow variables can only grow, and therefore termination is guaranteed. Okay, since the initial value is empty, live variables analysis converges on the smallest possible set, which is the most precise result of live variables analysis. So if I declare additional variables to be live, that's okay, but it is imprecise. It's an error. It's an error, but it's a harmless error. I would like to minimize this harmless error, and the way to minimize this harmless error is to compute as small a set as possible at every program point. Okay, how many iterations do we need for reaching convergence? Again, interesting questions, but we are not answering them here. Okay, going beyond live variables analysis, do the sets always grow for other data flow frameworks? In general, what is the complexity of round robin analysis for other analyses? That's again a question that we will not be able to answer. I'm just trying to raise these questions to make you aware that there are many interesting deeper things that go in this subject, for which there are very interesting answers. But let's come to this. Do the sets always grow for other data flow frameworks? So the answer is no. We will see a data flow framework where the sets do not grow. In fact, they shrink, start from a universal set. Okay. Now, these are two important slides here. Conservative nature of analysis. Help me answer these questions. So, absolute n returns the absolute value of n. is Y live on the entry to block B2? Look at the program and help me answer this question. Yes or no? Yes? Should it be live? So we are saying that there is a path here. If we look at this path, we find that the value of y is used. But will this path be ever taken? So the answer is this path is never taken, because if you are saying absolute value of x, it will never be negative. Okay. So this path B1, B2, B3 is an infeasible execution path. That's never going to happen at runtime. Turns out that in our data flow analysis, unfortunately, we cannot characterize this very precisely. There are some analyses which try to do it. There are some analyses that tell you what are infeasible paths. One of very interesting PhD that one of my students did, again a senior scientist from TCS Research, his PhD involved given infeasible paths, how can you exclude the effect of infeasible paths and make your analysis more precise. For example, if I knew that this path is infeasible, I would not declare y to be live. Okay, in this situation it's very easy, but in the general, given any data flow analysis, given any infeasible path, how can you exclude the result of infeasible path? That was the topic of his PhD thesis. Okay, so a compiler makes conservative assumptions, assuming that all branch outcomes are possible. Okay, consider every path in the control flow graph as a potential execution path, because of which we are covering more behaviors than are actually possible at runtime, which means that our result will never be unsound. It may be imprecise. So declaring y to be live at the exit of B2 is an error, which is a harmless error. It's not a harmful error. What would cause a harmful error? If I miss out a path. If I miss out a path, then I may not be able to declare something as live that actually should have been live, the first case, right? Then it would be a harmful error, right? So our analysis concludes that y is live on entry to block 2. So now there is a possibility of something called a path sensitive analysis. We are doing flow sensitive analysis. We can also think of a path sensitive analysis where the data flow values along different paths are kept separate. As you can imagine, that's very expensive, because number of paths could be exponential in the number of conditions in the program. So therefore, although theoretically path sensitive analysis is possible, of course in the presence of loop, path sensitive analysis is infeasible, because you have infinitely many paths depending upon the properties that you are trying to find out, not be feasible. Practically, people rarely do path sensitive analysis, which means that people do path sensitive analysis, but rarely. It's not never. Sometimes they do. There are situations where path sensitive analysis is useful. Okay, let's look at another example. Okay, is D live on entry to block B2? What do you think? Yes or no? No? I have this path. What do you think should happen? I mean, I do have this path along which D is live along which D is used. Huh? It's not a feasible path. Mm-hmm. Yes. So this path is infeasible execution path. If x was negative here, it will continue to be negative here because there is no assignment to x here. Right? So I may take this path, but I cannot take this path. Right? This is another example of an execution path. There is a very interesting data flow analysis called branch correlation analysis, which says that if this branch was true here, next time you have a branch, will it always be true? So do the branches correlate? So if you can do branch correlation analysis, then you can figure out infeasible paths in a program, right? So now dual question, is D live on entry to block B3? So obviously yes. Is C live on entry to block B3? So the question is this path feasible or infeasible? That's the question. This is feasible because the value of x may be changed. So maybe it was positive here, but here it could become negative, right? So again, once again, a compiler makes conservative assumptions. Our analysis is path insensitive. Okay, it is flow sensitive, but it is path insensitive. Okay, it is flow sensitive because information is computed for every control flow point separately. Okay, so we assume that all paths are potentially executable, and we talked about, yeah. So we'll start with, we'll look at available expressions analysis later. I think we still have another few minutes for tea to come. I want you to pick up the tutorial problems on live variables analysis from your Google Drive and try and do them. So let me show them to you. ACM. D2. Yeah. So please pick out from your, please go to Google Drive and, oh, I don't have internet here, I don't know why. SRMIST. Okay. Download. Still not. Okay. Yeah, maybe. Let me just do this. Yeah. Yeah. Please go to Google Drive. There are these tutorial problems. Please pick up a problem on live variables analysis. Please try to do it. Yeah, I have to say something, yeah. 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 Yeah, connected. Yeah. Thanks. if the tea coffee has come, maybe we can break and can have coffee and come back as soon as possible. So, welcome back after the tea. We have solved many problems on live variables analysis. There are more problems in the tutorial sheet, and maybe you can solve them later because most of you seem to have got a hang of what live variables analysis is. So I thought we should move on to the next analysis to give you some contrast uh, between the two analyses. So let's talk about available expressions analysis. We saw in the morning today the optimization called common subexpression elimination. So available expressions analysis allows us to perform common subexpression elimination. So let's look at that, and this discussion will be short because we have covered most of the concepts that we wanted to cover with live variables analysis. So let's start right away defining what is available expressions analysis. So we say an expression E, we refer an expression E is available at a program point P if every path from program entry to P contains an evaluation E of E which is not followed by a definition of any operand of E. So you can start finding parallels with the definition of live variables analysis. You can see the contrast as well. So like live variables analysis, availability of an expression is also a property that is specific to a control flow point. An expression may be available here, may not be available here, may be available somewhere else. So this is also a flow sensitive analysis. So that's a parallel. Second is, here we talk about path from program entry to P. For live variables analysis, we talked about path from P to exit. So live variable analysis talked about the future of execution. Available expressions analysis talks about the past of execution. Available expressions analysis says from start to this point, what are the expressions that have been computed. So that's difference number one. Difference number two, live variables analysis put the condition saying that if the condition is satisfied along some path, it's okay. Available expressions analysis says no, this condition must be satisfied along every path. It's not okay to just say that the condition must be satisfied by only one path, and we will see the reason why this is so. Okay, and how is the availability generated? In case of liveness analysis, liveness was generated by a use of a variable which was not preceded by a definition. In case of available expressions analysis, availability is generated by evaluation of an expression which is not followed by a definition. So you can imagine that available expressions analysis is kind of a forward analysis. So let's take example number one. Let's take first example. Is expression A star B available here? Yes or no? Based on these conditions? Yes? Yes. So how does it help in common subexpression elimination? If I had an A star B computed here, and if I had expression A star B available along all paths, I could simply store the result in a temporary and use the result of the temporary here. That's how it helps in common subexpression elimination. That is the reason why we talk about every path. So if we want to replace this, then the value of the expression has to be available along every path. So if I have one path in which A star B is not available, then I can't eliminate A star B here because along that path the value of the expression is not available. So this is the reason why we talk about every path rather than some path, right? So A star B is available. What about the second example? Is it available at P? No, because it is modified here. So here, so what is the meaning of availability of an expression? The meaning of availability of an expression is the following. Let me just use the board and write it intuitively. The meaning of availability is, I am saying that an expression A star B is available at P. So I am talking about expression A star B, and there could be multiple paths reaching A star B. So what I am trying to say is, if the expression is available, what it means is that along every execution path, so suppose we take this execution path. This expression is A star B is available, then in this execution path, the value of A star B computed here is same as the value of A star B computed here, because no operand has been modified. This property holds for every path. So the value of an expression computed at a program point is same as the value of the expression computed in every the previous occurrence of the expression in every path. It does not say that the value of the expression is same in all paths. So it's not that this value of A star B is same as this value of A star B. What it means is, at this point, if the program execution were to follow this path, this value will be same as this value. If it happens to be this path, then this value is same as this value. If it happens to be this path, then this value is same as this value, which means that the previously computed value can be reused. I can store the value of the expression in some temporary variable and use that temporary variable. So that is how I can perform common sub-expression elimination. As you can see, I cannot do that here. If I have A star B here, I can't promise that this value is same as this value, because maybe A has changed here, right? So that's the intuition behind available expressions analysis. What about the third example? Is the expression A star B available at P? No, because along this path the expression not at all evaluated. So we want that the expression be evaluated along every path, and we want that along every path the evaluation of the last evaluation of the expression should not be followed by a redefinition of any of its operands, right? So here A star B is not available. Okay, now we can directly jump into data flow equation. They have the same form, generation and killing. So here an expression E is evaluated in a basic block if it's available, if its availability is generated, if it is evaluated in a basic block and it is not followed within the basic block by a definition of any of the operands. So I have A star B, and within the basic block after this evaluation neither A nor B is modified, then the availability of the expression is generated, right? Similarly, killing of expressions, the availability of an expression is killed if any operand is modified. This is how we define gen and kill. And then we have data flow equations which are similar to live variables analysis but not the same. There are significant differences. In this case, we define at the entry of a program this boundary information. So if you are talking about expressions involving local variables, no expression is available at the start of the program, right? So if it's a start block, then so remember in live variables analysis we talked about the out being empty set at the exit. Here we are talking about in being empty set at the entry of the program. So these are duals of each other in some sense, okay? And then at in n, for a node n, we say because we want the expression to be available along every path, therefore we take an intersection. Therefore we say that if the expression is available at the exit of a predecessor, the same expression must be available at the exit of every predecessor for it to be available at a node, and therefore we simply take intersection, right? So here in live variables analysis we took a union, here we take an intersection. In live variables analysis we talked about successors, here we talk about predecessors. So live variables analysis is a backward data flow problem, available expressions analysis is a forward data flow problem. Live variables analysis is a union data flow problem, available expressions analysis is an intersection data flow problem. Live variables analysis talked about variables, available expressions analysis talks about expressions. So there are similarities and there are differences. At an abstract level, they are all similar. In fact, turns out that when we talk about data flow analysis at an abstract level, there is a very general form of data flow equations from which all data flow analysis derive. They have a very nice structure, they have a very nice theory, they have very nice algorithms. There are lots of parallels, insights that you gain from one can be used in the other. But here we are only looking at instances of data flow analysis. We're not looking at the general theory of data flow analysis. So having done that, now how do we compute the expressions available at the exit of a block? Simple. The expressions that are available at the entry, from that you remove the expressions whose availability is killed, and then you add the expressions whose availability is generated. So we have the expressions available at the exit of a basic block, right? So here now we introduce another form. We introduce this flow function fn associated with block n, which has this form. Fn of x, x is its argument, so we say x minus kill n union gen n. The interesting part is that this gen and kill are constant properties of a statement. Like live variables analysis, for available expressions analysis also, gen and kill do not depend on the incoming information. They are constant. There are some interesting analyses where gen and kill are not constant. The examples of these analyses is constant propagation, strongly live variables analysis, or pointer analysis, heap reference analysis that we saw in the morning. These are the analyses that are more advanced. The analyses that we are looking at are the simplest of the analyses. Okay, so this is the form of data flow equation, and here in and out n are sets of expressions, and boundary information is empty set for expressions involving a local variable. So this is the data flow equation, and well, so how do you use it for common sub-expression elimination? If an expression is available at the entry of block, so the first thing is, in order for us to eliminate an expression as an instance of a common sub-expression, first of all the expression has to be available at the entry of the block. Okay, then we must have a computation of the expression within the block. It's required. So if you don't have a computation of the expression, what are you going to eliminate anyway? So if you want to eliminate, there has to be a computation of the expression. The third requirement is that this computation of the expression should not be preceded by a definition of any of the operands. Okay, so we define this, I mean we can ignore this, don't worry about this formula, but what it essentially says is that, let me explain it on the board. So what we are essentially trying to say is that if we have a basic block here and we have a basic block and we have an occurrence of A star B, and we are asking, is this A star B an instance of common sub expression? Can I eliminate this A star B? For that, what we want is, along all these paths reaching here, A star B should be available. Then in this path, neither A nor B should be modified. Because if A or B is modified in this path, then the value of this expression may not be same as the value of this expression. So with these two conditions, we say we can perform available expressions analysis. So here, for example, we talk about upwards exposed, downwards exposed, etc. So here this computation of A star B is downwards exposed because it is not followed by a definition of A or B. It is not upwards exposed because it is preceded by a definition of A. This computation is upwards exposed because it is not preceded by a definition of B or C, but it is not downwards exposed because it is preceded by a definition of C. And this expression is neither upwards exposed nor downwards exposed because this expression is preceded by a definition of A and followed by a definition of C. So this is a notion that you should keep in mind. When we talk about availability of the expression, we want in the set gen the expressions that are downwards exposed, whereas when we eliminate the expression, for example here we want this expression to be upwards exposed if you were to do common sub expression elimination. Okay, that is all that is to available expressions analysis. Upwards exposed, downwards exposed mean the expressions are exposed because they are not covered by a definition of their operands. Meaning they are, so here Upwards exposed meaning the value of A star B here and here will be same. Downwards exposed mean the value of A star C here and here will be same. So if it's computed somewhere in the basic block and expression A star B is upwards exposed, meaning the value of A star B within the basic block and the start of the basic block will be same. That's the meaning of upwards exposed. Meaning of downwards exposed is value of A star B here and at the end of the basic block will be same. That is downwards exposed. So downwards exposed is what we use in generating the availability. Upwards exposed is what we use in eliminating common subexpression elimination. So here for example we require this A star B to be upwards exposed. If it is not upwards exposed, then I cannot do common subexpression elimination for this, right? That is the meaning of downwards and upwards exposed. Okay, so time for a tutorial problem. So let's just look at the result. So now here for a change we use a bit vector notation because it's cumbersome to write. So sets and bit vectors are interchangeable. In fact, the data flow analyses that we are looking at are classically called as bit vector data flow analyses because we can use bit vector operations to perform these analyses. So we can have a bit vector, we can take an intersection of the bit vector, we can take a union, or an AND of bit vectors, and that's how we can perform these analyses efficiently. So here I want you to go through the gen and kill and explain to me why the gen and kill of a node is what it is. Please go through it and let me know. Repeat. Bit vector data flow framework. The question is here I want you to look at, so I have computed gen and kill sets here. There is a set and there is a corresponding bit vector representation. There are 4 expressions A star B, B star C, C star D, D star E. So we represent it with a bit vector where A star B is the first expression, B star C is the second expression. So here because we have E1 and E2, therefore the bit vector is 1 1 and E3 and E4 are not there, so therefore it's 0 0. So the point is bit vector and sets are interchangeable. You can always represent a set by a bit vector and a bit vector by a set. Now the question is, I want you to go through this program and for each node I want you to justify why the set gen is like this or why the set kill is like this, or alternatively why is this bit vector all zeros and why is this bit vector 0 1 1 0. Yes, 1 means expression is available, 0 means it's not available. Here 1 means expression generated, here 1 means expression is killed. So 1 means it belongs to the desired set, 0 means it does not belong to the desired set. So set and bit vectors are just a form of representation. So now I want you to look at the gen and kill, whether you look at the set notation or the bit vector notation doesn't matter. Yeah. What is the meaning of expression holding the variable? Expression in which the variable is an operand, right? Yes. So the value of that expression may change and therefore the availability of that expression is killed. So I want you to explain gen and kill from there. For 1, why is this way? For 2, why is this way? So someone tell me, why is the gen for node 1 E1 and E2 or 1 1 0 0 and why is the kill empty set? For node 1? Yes, E1 and E2 are evaluated in node 1 and they are not followed by a definition of any of their operands. So therefore they are in the set gen. And why is the kill set empty? No, there is no assignment, no variable is modified. Wonderful. What about node 2? only E3 is evaluated, no, nothing is modified. What about node 3? Nothing is evaluated, but for which expression the availability is killed? Hmm. For the expression for which C is the operand. So here gen is all 0 zeros and E2 and E3 are killed. So we have 2 and 3. So second and third positions are 1. Here 3 and 4 are killed. The third and fourth positions are 1. Right. So similarly, so we have gen and kill here. Okay. So we'll talk about availability later, but let's try to do this analysis. So here, because it is an intersection problem, we start with the universal set as the initialization. Live variables analysis was a union problem. We start with the smallest set. Here we start with the largest set and let the set grow. And now that should immediately tell you, using the same intuition, the analysis will terminate, because the sets are going to shrink at some point of time, and at some point of time the worst that can happen is they become empty set. After that there will be no further change. So termination is automatically guaranteed. So now this is the initialization, and the start we are saying no expression is available, and now we assume that all expressions are available everywhere. So this is the first iteration. Please tell me what change will happen in the second iteration. Please work it out. Let me write the equations here. These are the equations. So what will be the change in the first iteration? Where will be the change in the first iteration? So these are the values that have changed. Please compare whether you're getting the same thing. This is the result of the first iteration. Anyone getting something different? Anyone who's getting a different result after the first iteration? Same? Okay. Let's look at the result, the final result, the second iteration. Oh, there's only one iteration, is it? Oh, sorry. Yeah. Yeah. This is the final result. Oh, I have. Please see if you are getting this result. What happened?
He's saying how to know that where the changes.
So I let me just check if I have anything else here. I don't think I have anything else here. Yeah, so there are more tutorial problems here, and the results are also here. So all I want you to do now is, yeah, maybe, yeah. So just we'll look at this slide and then we'll go back to tutorial problems. So the important point is data flow equations do not require a particular order of computation. So here we are doing in a forward direction. For live variables analysis we were doing them in a solving them in a backward direction. As far as the final result is concerned, it doesn't matter in which order you do. The order governs efficiency of solving. How many traversals do you need? That is governed by the order. It does not govern the solution. In fact, there is a method called method of chaotic iterations, which randomly picks up a node and calculates the data flow value. And people have found that in some cases that works better. I don't know why people do such things, but they do, right? So there are methods such as this. So the point is, the actual algorithm of performing analysis is not is different from the specification of the analysis. So data flow equations define mathematically what is it that you wish to compute, how you compute, in which order do you go, do you use round robin algorithm, there is something called work list algorithm, there is something called elimination algorithm. So there can be many different ways of solving the data flow equations. But once we define the data flow equations, we are essentially separating specification from implementation. We are essentially separating specification from the algorithm. So the whole idea behind this data flow analysis, the way I would like to project is, if you come across somewhere else, you will see that the presentation is completely algorithmic. I would rather want presentation to be declarative. So I can intuitively describe, I can formalize it, I can mathematically define what I want to do, and then I am free to choose any algorithm that computes it. So the separation between specification and the implementation is something very useful and very important, because it gives us many degrees of freedom. It allows us to choose different algorithms that can compute the same thing. I just want to define here what is it that the algorithm is supposed to compute. How it is being computed, I don't care. There can be different ways of doing it. Okay, so that's the important observations. Then initialization govern the quality of the solution. Turns out that you can start with any initialization that you want. The result that you get is a very beautiful result. No matter what initialization you start with, the result that you get is always going to be sound. Okay, any fixed point, there is a nice formal proof which says that any fixed point of a data flow equation is a sound solution, but its quality may not good. So you may have, if you choose a different initialization, you may get errors, but those errors are harmless errors. They are never going to be harmful errors, so long as the values are consistent with each other. What does a fixed point say? A fixed point says that the data flow values that I have computed are consistent with each other. So if I have x here and if I have y here, x and y are consistent with each other, where consistency is defined by their relationships specified in the data flow equations. So that consistency guarantees soundness. Okay. However, the quality may not be good. For example, I begin with no expression being available anywhere. So let's take this example. Here, supposing I begin with no expression being available here. Okay. So here I assume 0, 0. So I will say, okay, no expression is available here because of that reason. So therefore, even though A star B and B star C are available here, we might say no expression is available here, and we may not be able to do available expressions, and we may not be able to do common sub expression elimination. So the result will still be correct. Not being able to optimize program is not wrong. It's not a harmful thing as far as correctness is concerned. Okay. So what happens is, if you choose a different initialization, and the same thing happens for live variables analysis. If you use universal set as the initialization, you might have more variables declared as live, and we have seen that that's actually a harmless error. Okay. So the moral of the story is, initialization governs the quality of the solution, not the correctness of the solution. Similarly, the choice of order of evaluation governs the efficiency of the solution and not the correctness or the quality of the solution. Okay. So initialization, when we say initialization, we are talking about the initial value that we use at the internal nodes. Then we have this something called boundary information, which depends on the semantics of the calling context. So if you're talking about local variables, then we might want to say that, look, no variable, no expression is available at the start, no variable is live at the end. And if you're doing possibly uninitialized variables analysis, we will say every variable is uninitialized at the start. So that's the semantic information. So the choice of boundary information governs the correctness. If we use the wrong value there, our result may be wrong. So this value is associated. So this may cause unsoundness if you use the wrong value, and this value is associated with a boundary node. Okay, and this is specified by the data flow equation. What is the boundary node? For a forward analysis, the entry of the function is the boundary node. For a backward analysis, exit of a function is the boundary node, right? So that's where the semantic information, this boundary information, is associated. And that is all as far as observations are concerned. There is a third analysis that I was hoping to cover, but we will not cover that analysis. The slides are here. Instead, I would rather have you solve the tutorial problems that have been given to you for live variables analysis and available expressions analysis, because I want you to understand things more deeply and know two analyses well, rather than having three analyses and know them superficially. So therefore, I am not going to cover this, but the slides have been given to you. Please go through them at your leisure, and if you have any questions, you can always ask me questions. My lectures on this are available on YouTube. This was in the COVID time when I was forced to record lectures. So there are obviously old lectures, but there isn't much change in this part of the course. Changes are in the later part of the course. So you can even watch the lectures on YouTube. You can use these slides. You can send me an email. You can ask me your questions later. But and study this on your own. I won't cover this. Whatever 45 minutes we have now left, I would want you to solve the tutorial problems with the help of the TAs. Please solve the tutorial problems of live variables analysis and available expressions analysis. You are also free to solve the tutorial problems given here, because for them the solutions are here and you can compare the solutions. They are available to you, right? So that is all that I would like to cover as far as the lecture part of this module is concerned. Please solve the tutorial problems, and I promise you I won't see you tomorrow because I would be gone. So I won't bother you anymore with this, but please do solve the tutorial problems that I have given to you. Yeah. Maybe I'll do some work myself now. I'll just disconnect it. You can use your laptop and access the tutorial problems.